In this video, you are going to learn about the Bohr model. Earlier this semester, we learned about the Rutherford experiment, and it proves that the preferred model for an atom will be positive inside and electrons somewhere going around it. Let's say if the electrons are going in a circular orbit or circular path, so electrons are over here. All right, if the electron is not moving and if I have one positive inside or many positive inside, what will happen? Positive sees a negative, it's going to attract each other, and if it's not moving in the next second, what will happen? The positive will be here, the negative will be here, and they will close to each other. So what happened is, to keep certain distance, this electron must be moving. In other words, the energy of attraction over here, according to Coulomb's law, it should be equal to, the force should be equal to, okay, that's a constant, charge 1, that's the charge of the nucleus, charge 2, that is the charge of the electron, and divided by r squared, where r is the radius or the distance over here. That will be equal to, when the electron is circulating the nucleus, then we have a centripetal force which is equal to m, the mass of the electron, times v, velocity of the electron, v squared divided by r. So this one is called the centripetal acceleration. Okay, so that's about the classical mechanics of an electron that is circulating a positive charge inside or many positive charge. The second concept that I would like to introduce to you is called the de Broglie wave. Before, we talked about that a photon carries momentum, and that is by the Compton's experiment. So now we can actually quantify what the momentum is. According to de Broglie, momentum P, that is equal to a Planck constant divided by the wavelength lambda. This equation also works for other particles, small particles. And if you look at this one, momentum, classical physics says momentum that is equal to mass times velocity. Okay, so bear in mind that momentum of something that is very light, especially for particles, it also follows the de Broglie relation over here. It is momentum equal to Planck constant divided by the wavelength of a wave. Okay, so we just bear that in mind. The third thing is, actually, this will be the introduction to quantum mechanics. What happened is, according to Bohr, so he suggested when an electron moves circling the nucleus, it actually forms a wave, standing wave. That means over here, n lambda, the number of wavelength will be exactly equal to the circumference of this circular path. So that will be equal to 2 pi times r. So this is the introduction to quantum mechanics. That means something is quantized. What do I mean by quantized? Quantized means it's not continuous. It's a discrete level. For example, when you play piano, you will see the key over here. Okay, so you press this key and you press this key. That will give you different notes. But when you play violin, okay, so if you put your finger here, you can move your finger very small and you can get a continuous frequency or pitch. So over here, you can only get 2 different frequencies, but a string can give you continuous frequencies. We call this type of discrete level is called quantized. So in the Bohr model, what happened is, what he proposes, n lambda will be equal to 2 pi r. So in this case, if we isolate lambda, we are going to get 2 pi r divided by n. And if you put into the de Broglie relation, momentum is equal to Planck constant divided by lambda. If that is the case, then momentum will be equal to nh divided by 2 pi r. So momentum is quantized and energy is also quantized. That's the beginning of quantum mechanics. Okay, so what are we talking about here? If we combine all the above, that's called the Bohr model. So what from the Bohr model, what it said is, inside the nucleus, it will be a positive charge. And electrons can only go in a circular path surrounding the nucleus. But it cannot be going anywhere. It can only go in certain radius. For example, when n equal to 1, the electron can stay here. When n equals to 2, the electron can stay in this radius. It can only stay in certain radius because the radius is quantized. And once it stays in certain radius, it will have certain energy. And the energy is equal to this by this equation. The radius is given by this equation. Let's look at it. What happens when the electron is over here? Let's say for hydrogen, for example, hydrogen atom, where inside there will be one positive charge, that is the proton, and out here is an electron. When the electron is closest to the nucleus, or when n is the lowest number, we call that ground state. So ground state means when n is the lowest number, starting from 1. If this electron jump to the other level, and that is called the excited state. The ground state will have the lowest energy. The excited state at different energy level will be have different energies. For example, let's plug into here. Let's say when an electron is from the ground state and it goes to the next level, let's say it goes to n equal to 3. What happened? It's not stable. It would like to fall back here. It would like to come back here. So how can an electron come from the ground state to the excited state? There are many means. It can be thermal energy. We can heat it up. Or we can apply high voltage so it can absorb certain energy and go up there. But when it falls back, it's going to release the energy. And this type of energy is electromagnetic wave. So that will be the type of energy it will release. In order to see how much energy it can release, we can look at this one here. Let's say, for example, I would like to know the energy when it comes from n equal to 3 and fall back to n equal to 1. I would like to know how much energy is released. Okay, so we put in the formula here. E of 3 at the third level will be equal to minus k. Z in this case is the charge of the nucleus. If it's a hydrogen atom, then the charge is 1. If it's helium, then the charge will be 2. Okay, so we are talking about a hydrogen atom now. So Z is equal to 1, and then I have to divide it by n squared. That means 3 squared. Okay, so that is equal to negative k times divided by 9. All right, so let's calculate about what happened when n equal to 1. So plug into that, it is equal to negative k divided by 1 squared. So that is equal to negative k divided by 1. So what is the energy difference? So delta E will be equal to E at level 3 minus E in level 1. So that is equal to negative K divided by 9 minus K divided by 1. Minus minus, because there's a minus here. Okay, so I can flip this term. Minus a negative number is same as a positive number. So it's K divided by 1 minus K divided by 9. Okay, so that would be the delta E. So in general, for hydrogen atom, what is the energy difference if an electron falls from an excited state to the ground state? The energy will be equal to a constant K. See, this one, so that's the initial state. So K divided by initial state and initial square minus K divided by final and final square. Yes, you can copy down this formula now. All right. So what happens if we just plot the energy levels? Here's the plot. So this one shows the energy levels of an electron in hydrogen atom. So this one is ground state. We can put in energy, heat it up, so it can go to the next stage. That is n equal to 2, n equal to 3. So the electron, when it's over here, there are options. It can either jump over here from level 3 to level 2, or from level 3 to level 1, or from level 2 to level 1. And therefore, we should expect to have many different delta E's. And each of the delta E, it can show up in an energy graph, and it look like this. For example, hydrogen over here, hydrogen, we can see different energy levels over here. We can see the spectrum. We can see the lines over here. And with different elements, we can see the lines in different locations. And by using this principle, we can use to identify unknown materials, unknown elements, because we just have to excite it. We just have to put in energy, thermal energy, electrical energy, or other types of energy. When it releases energy by falling from an excited state to the ground state, we can measure what that delta E is. And based on that, we can identify unknown element. Let's say we put everything in the database and we just have to compare the spectrum. Let's review and see what we learned from the Bohr model. First, it says that electrons actually travel or move in a circular path, in a circular path. Okay, and secondly, electron energy is quantized. Okay, and thirdly, momentum, energy momentum is quantized. And number 4, the radius is also quantized. That means there are only certain allowable radius. You cannot have the radius anywhere you want. Okay, so now let's do some exercise. Over here, number 3, the Bohr model of an atom. Okay, electrons travel in a circular path called orbitals. Okay, it travels in a circular path, but it doesn't call orbitals. Orbital, in the future you will learn, it has other meanings. Okay, number B, electrons have any energy? No, it can only have certain energy. It's called quantized. C, electrons' energy are quantized. Okay, that is good. D, electron paths are controlled by probability. In the future, we can hear something else about it, but it's not about the Bohr model.